All right, guys. So I sent you guys a survey about the class, the rest of the class and stuff, and most of you guys said that you guys wanted me to record like a small video, just like a background information about the investigations that we're gonna do, so you guys can, write the report and finish the proposals and the pre-labs and stuff like that. So I know there's a lot of confusion about what things are due and stuff. I'm gonna send an email with kind of detailed information about what is due and what's not due for this week. But basically, the quiz will be due at 11:59 p.m. So make sure you submit it before midnight tomorrow, and you can just take a picture of it and then go on Blackboard on the assignment. You're gonna see quizzes, and then go to the folder that says submission, and then you send it, and I'll grade it. So just a picture, scan it, or whatever is fine with me. Just make sure you send it by the time that it's due. I also sent an email saying that the written argument one was gonna be due, but most of you guys actually turned it in before spring break. So I actually grade all of those, and I sent you guys an email with the graded picture of it or scan of it, so you guys can see and see where you got points taken off and stuff. So basically for today, if today was a regular lab, what we're gonna do was gonna be investigation 4, and we did the pre-lab last week about what is the composition of purple, 1 liter solution of purple pirate dye, and we did it in class. And basically the guiding question was, what is the composition? And we were basically just trying to find how much red and how much blue was in 1 liter solution of purple. And so that's what we were supposed to do today. So now with this online version and stuff, basically you have a video that you're gonna watch. It's gonna be either purple pirate 1, 2, or 3. And instead of you doing the experiment and stuff, somebody's doing it for you, and they're giving you the data, right? So then you take that data just as if you were to perform the experiment, and you do the calculations, the data analysis, and then remember after we finish that part, then we will grab the whiteboards and fill them up, write the guiding question, the claim, evidence, and justification, and then put it up in the bench. And one person had to stand there and talk about it while the others will go around the lab and ask questions. So instead of doing that, what we're gonna have is the group is gonna have a PowerPoint presentation of 4 slides, and it's gonna be like a whiteboard argumentation type of thing, and you will submit it on your discussion board, and you'll comment to other people and stuff, just like what we used to do in the lab. But this time it's gonna be online. So that's what basically we're gonna be doing this week. And just to recap, the week before spring break, we actually did pre-lab number 4, sorry, and that was to find the relationship between absorbance and molarity. And remember, molarity is the same as concentration. So we just want to see what the relationship between absorbance and some concentration would be. And I gave an example of, so imagine you have two containers, right? 2 glass containers, and they're full. One of them, container A, is full of some particles, so you have solution of something, but it's full of it. Whereas container B don't have as many. It's pretty much just clear because you don't have that many particles of that compound that you have. So the solution is really diluted. So if you were to shine a light through it, on the other side, the solution that's more concentrated, you get less light than the one that's least concentrated, right? Because the light can go through more because there's not as many particles. So what we basically saw was that if the concentration increases, then the absorbance will increase. So we knew that was a positive relationship, and what we were trying to find in the lab was to see what type of relationship is it, if it was linear, quadratic, or so on. We actually found that the concentration of absorbance and molarity was linear, and we did that by finding the absorbance of a blue dye and a red dye. And basically what we did was we had a stock solution, one for the blue, one for the red, and we knew the molarity of it because it was right on the bottle, right? So we did a series dilution of the red and the blue dye. So we took 10 milliliters of that, put it in beaker A, then added 10 milliliters of water, mix it up. Then we took 10 milliliters of beaker A into beaker B, and then 10 milliliters of water, mix it up. Then we took 10 milliliters of B and added it into beaker 3 and added 10 milliliters of water and mix it up, and so on. So what we're basically doing was a dilution, and the point for that was because we wanted to create a graph. We wanted to plot absorbance and molarity, to see the relationship between those. So in order to do that, you gotta have data points. You gotta have data points on the graph so you can connect the lines and stuff. And we knew the molarity of the stock solution, and we found the molarity of A, B, C, and D using M1 V1 equals M2 V2. And we actually did that on page 58, where we filled out that table for blue and red. And so we knew the stock was some number. We took 10 milliliters of that stock. We made a new solution, which we don't know the concentration of. That was A. And the total volume of that solution was 20 because we have 10 mLs of the stock and 10 milliliters of water, which gives you a total milliliters of 20. So we solved for M2. Basically, we divided by V2 and isolated M2 to get that value. And we did the same thing for solution B, where we put the molarity of solution A here, and then 10 mLs, then molarity of solution B, which we didn't know, we found that one, and the total volume was 20, and solved for molarity of beaker B, or solution 2, and so on. So we found those concentrations, then we went to a lab and we found the absorbance of each one of those solutions using a colorimeter. And we set up the colorimeter depending on which dye we had. If we had the red dye, we put it at 470 nanometers, which is the absorbent, which is the wavelength that red absorbs light in. And then for blue, it was 635 nanometers. Then we got the absorbance value, which absorbance is unitless, meaning it doesn't have any units. Right here, this NM stuff is nanometers, and that's the wavelength of it. That's not the absorbance. So the wavelength at which red absorbs light was 470 nanometers. Then we got the absorbance of it using the colorimeter, which was without units. And then we put it in, we put the absorbance values on this part of your pre-lab. And then on the program, we connected the dots and made a graph. And basically what we saw was that the absorbance was linear. And the equation that we got was the absorbance for red equals, and I'm gonna come up with this number, so I don't know if they're right, but some number, the slope, which I'm gonna say is 3 times m, which is the x-axis, which in this case is called m, molarity, plus another number. And then we got another, well, for the blue, so we got two equations, one for the red and one from the blue. And we did this by doing a series dilution, putting the dots on a graph, creating a calibration curve, and we got this trend. When we did that, we also asked you to write the R-squared value. So the R-squared value, basically, it tells you how well your data fits, basically a linear fit. So basically how linear data is. So let's say the R-squared value for this perfect line right here is 1, and that's the maximum of the R-squared value you can have, 1, which means it's completely linear. And yours was a little curved or something, so your R-squared value might have been 0.990, which means it's kind of close to 1, so it's pretty much precise, right? If you were to have our R-squared value of like 0.621, then your line probably looks something like curved like that, which means it doesn't really fit a linear fit for your data. So when you guys are doing your argumentation stuff, you can use this as part of your justification. If you got a high R-squared value, then you can say your data is precise and if it's a linear trend, therefore your your findings are reliable. Another thing that we said was that these two equations are calibration curve equations, which means that you kind of calibrated a graph for it, for a blue dye and a red dye. And if I were to find, so let's say I want to see how much blue is in any solution, then all I have to do is just take that solution, put it in my cuvette, and put it at the wavelength of blue, 635 nanometers, and see how much absorbance that takes, right? Then when I get that absorbance value, I go to my equation that I got from the graph for the blue, and I plug that into the absorbance part. And then I solve for M. And that basically is telling me, hey, you have this concentration of this molarity of blue in this solution, whatever it is. Okay? So these curves are basically reliable because they're linear, so that's part of your justification as well. So that was from last week. That was kind of like a refresher so that we're in the same boat, and that's actually going to help us a lot for doing the argumentation for this week. So now this week is what is the composition of a 1 liter pepper solution. So so the week before spring break we finished the proposal number 4 as well, and the guiding question was what is the composition of a purple dye and what data what we're going to collect. Well, we discussed in the lab that this data is raw data that you don't do any calculations to. It's just data that an instrument spits out, or that you don't have to do anything to it other than just record it, right? So in the pre-lab, our data that we collected was the absorbance. So for the proposal, we talked about this and we said that the data that we we're going to collect was going to be the absorbance of red and the absorbance of blue. So the absorbance of red is going to be done at a 470 nanometer, and the blue one is going to be done at a 635 nanometer. So when you have the colorimeter, you set up the the wavelength, and that's going to tell you how much absorbance that is at that wavelength. So that's what we said we're going to do. And then we talked about how we were going to collect that data, and then if you watch the video, that's going to do the whole procedure for you. And then how are we going to analyze this data? Well, you got those equations from last week, right? So all you have to do is, I gave you an example, like you get the absorbance of red. How are you gonna know how much red is in 1 liter purple solution? Well, you get your purple solution, you put it in a colorimeter, and you set up the colorimeter to 470 nanometers, and that's gonna give you an absorbance. That's the absorbance that solution can absorb at a red wavelength, meaning that you can actually go back to your pre-lab, get that equation for red, plug that into the absorbance, and solve for M. That M value is going to be the concentration of red in that purple solution. So you will actually do the same thing for blue, and what you're actually finding at this point is the molarity of red in purple and the molarity of blue in purple, right? So that's part of the answer to the guiding question, but you also want to know how many grams per liter we have of red and blue in that purple solution. So if you go to page 59 in your task area right here, these two numbers